Welcome to this video on the law of sines and cosines. The law of cosines and the law of sines are formulas that are used to solve triangles that are not necessarily right triangles. Unlike SOHCAHTOA, which you may have seen in a previous video, the law of sines and cosines are formulas that work for any triangles, whether they're right triangles or not. So they're a little more general. We're going to look at these formulas first through an example of a problem where we know one angle. So suppose we're being asked to solve this triangle. Again, solving a triangle means to find all the missing angles and sides. So the first thing you want to do when solving a triangle is label your sides. It's worth noting, however, before we start, that pictures or diagrams in this type of venue, especially if you're taking one of my classes, will not be drawn to scale. I have the same triangle that I use for all the problems. And in fact, if you just look at this triangle here, ignoring the numbers, it looks like an equilateral triangle, which it has all three equal sides. But I'm not meaning to imply that these sides are equal. I'm simply not drawing the diagram to scale. And we do that for two reasons. One, sometimes we just don't want to take the time to draw diagrams to scale. It's a laziness issue, but there's a bigger reason too. We often don't draw things to scale because in higher mathematics, the triangles we're analyzing represent dynamic things that are in motion, and if side lengths are changing and angles are changing, and that's quite often the case in a calculus class, then there's no sense drawing anything to scale if it's not going to stay to scale the whole time. Nonetheless, figures not to scale. Moving on. So because I'm solving this triangle, I'm going to label all the things I don't know. I tend to use Greek letters for angles, not that you have to. Okay, now this may or may not be a right triangle because we don't really have a picture of the scaling. Maybe theta or beta is a 90-degree angle. But we simply don't know. And because we don't know, we cannot use SOHCAHTOA, and we cannot use the Pythagorean theorem. Those are both right triangle specific formulas. And you may recall, if you watched my video on SOHCAHTOA, or right triangle solving, you may recall that we had 8 equations of the triangle, and out of those 8, the only one that was general to all triangles was the 180-degree rule for triangles. So again, without any evidence here, we don't have the option to use SOHCAHTOA or the Pythagorean theorem. When we don't have these options and we don't know whether we have a right triangle or not, we use formulas called the law of sines and the law of cosines. These are the equations for the law of sines and cosines. You may notice that they have a bunch of A's, B's, and C's sprinkled throughout. These are the traditional ways of writing them. But if you look at our problem, of course, and this is almost always the case, there won't be an A, B, or a C in your problem. So how are we going to use these formulas? What do A, B, and C represent in this situation? You'll notice also that some of the A's and B's and C's are uppercase and some are lowercase. Here's what's meant by these formulas. The letters, the capital letters A, B, and C, represent angles. And they can be any angles that we want. For example, A could be 35 degrees, A could be theta, or A could be beta, and likewise for B and C. But once we've chosen those, the lowercase letters, which are the side lengths, must represent the sides opposite to angle A, B, and C, respectively. And so, to give you a more concrete example of what I mean by opposite, here's one way that I can interpret the law of sines here. Notice in the diagram in the upper right corner that the 35 is opposite of the 12, and beta is opposite of the 10. And that correlates to be version of the law of sines that you see there. So, like I said, capital A and capital B can be anything, but lowercase a and b must be the side lengths of the opposite sides to those particular angles. But this isn't the only way I can set up the law of sines. I don't have to use 35 and beta. I could use 35 and theta. And again, you can use whatever angles you want in the law of sines, 2 out of the 3 anyways. And you can use any 2 angles you want in the numerators, but the denominators must be the corresponding opposite sides to the angles that you chose. So you'll notice in the first 2 renditions of the law of sines, I chose 35 and beta in one of them, 35 and theta in another one. But there's another way to write the law of sines for this particular situation, and that's to use beta and theta. And again, the denominators are the corresponding opposite sides. Well, all 3 of these are valid for this triangle. And it turns out for any given triangle, you can write the law of sines 3 different ways. Now, which one of these is going to be helpful and how are we going to solve? Well, we're going to get to that later. Right now, I'm just guiding you through a process where you can write out multiple equations for any situation. Let's do the same for the law of cosines. This is one way to write the law of cosines for this particular triangle. Notice in the law of cosines, there's only one capital letter, and that's the capital C at the end with the cosine argument. And for capital C, you can choose any angle you want as long as lowercase c is the opposing side length to that. And then once you've chosen that, the A and B side lengths are the other 2. So you'll notice in this first rendition of the law of cosines, I've chosen beta as my angle. But because I chose beta as my angle, I had to choose side length 10 as my side C. In other words, you have to, whatever angle you choose at the end of your formula in the cosine, you must choose the corresponding opposite side to start your formula. Now, this isn't the only way that I can write the law of cosines. Here I wrote the law of cosines using beta as my angle, but I could also use it with theta as my angle, which is fine. This is correct also. But notice, if theta is my chosen angle in the law of cosines, then I have to start my equation with x. Reason? X is the side opposite theta, as you'll notice in the diagram. Well, here I chose to start with beta, and then I chose to start with theta, but I could also choose to start with a 35-degree angle. This is also correct because I've started with an angle, I've ended my formula with an angle, 35 degrees, and I've started my formula with the 12, which is the side opposing the 35-degree angle. Now, if you're a little confused at this point, and I wouldn't blame you if you were, it's because there's so many different ways to write out these formulas. In fact, in general, we can say that when you're given a triangle, you don't know whether it's a right triangle or not. There are 6 formulas that can be written, 3 using the law of sines, and 3 using the law of cosines. Now, myself, having lots of experience and having worked these problems since 1983, I'm not likely to write out all 6 formulas. But if you're very new to this and don't have a lot of experience or intuition, I recommend writing out all 6 formulas at first. What will happen is, over time, the need to write out all 6 will diminish. And eventually, through enough experience, you will look at a problem and instantly know which one of the 6 formulas are going to be the most useful to you in that particular situation. But you can only develop this intuition with practice. And you'll notice that it will arise over time, or it won't. And if it never does, then write out all 6. Here's a helpful hint though. After you've written out all 6, don't use any formulas that have 2 or more unknowns in it. Notice the formulas here. You may see them in pink. Notice the formulas that have 2 unknowns in them. Those are not going to be very algebraically easy to deal with unless I made a system of equations out of any 2 of them, and it doesn't seem practical to use those. The formulas in pink are correct, but they're not particularly useful to our needs. So that brings me down to these 2. And it raises an interesting question. Which formula should I solve? I could solve one of them. I could solve the top one for beta. I could solve the bottom one for x. In fact, I would seem to get 2 pieces of information that way. But I am not going to solve that equation for beta right there. Solving that equation for beta actually introduces a very annoying complication. Imagine how we're going to try to solve that equation for beta. I would probably cross multiply by 10, but wouldn't I at some point have to use the inverse sine function to solve for beta? Well, here's the problem with that, and here's why I'm not going to do that. When you're going to use an inverse sine function to solve for beta, it's only a practical option if we happen to know that beta is an acute angle. If I knew that beta was an acute angle, that would be an easy thing to do. I would cross multiply and eventually isolate sine of beta and use the inverse sine. An inverse sine is a great function to solve for the angle inside of a sine, as long as you know that that angle is an acute angle, in other words, between 0 and 90. But I don't know that beta is between 0 and 90. I mean, in my not to scale diagram, it appears to be, but that doesn't mean anything. And so without the knowledge that beta is an acute angle, I don't like to use the law of sines, because inverse sine is an annoying function to deal with when you don't know that that angle is acute, and we don't know that. So that means I'm going to start this problem with the only viable equation, and that's going to be the law of cosines in this case. So now that I've sifted through my 6 equations, eliminated 4 of them for having 2 unknowns, and eliminating 1 of them because I knew that it would be complicated by inverse sine, I'm now ready to start the algebra. So let's examine the algebra on how to solve for x. First of all, I can make some simple modifications. I can do 12 squared and 10 squared. That's simple. Furthermore, I can multiply these 2 numbers together. So I've got a calculator here in my hand. I've got it in degree mode. The cosine of 35 is about 0.82. And so when I do 20 times 0.81915, I get some big decimal. Now, you'll recall from algebra class, when you're solving an equation with an x squared in it, you want to set it to 0. So I'm going to set my equation equal to 0 by subtracting 144 from both sides. And I'm going to rearrange my terms, as we often do in algebra. And what you'll notice here is that we have a quadratic equation. And we can use the quadratic formula where a is 1, b is negative 16.38304, and c is negative 44. So the algebra is not shown here, but what I did was I plugged in my numbers for a, b, and c, and these are the 2 things that I got. It shouldn't surprise us that we got 2 answers, because the plus or minus sign in the quadratic formula indicates that we'll get 2 answers. Well, x is a side length, so I really don't see the meaning of the bottom answer here, that x is negative. I'm going to discard that one, and interpret this as x being approximately 18.7. So what I've done now is I've solved for one of my unknowns. Now that I have x, I can use the value of x to go on and solve for theta and beta. So, once again, not knowing if we have a right triangle or not, we're going to start out with the options of the law of sines and cosines. I'm going to try the law of cosines again this time, only now that I know x, I have an option of using that information, which I didn't before. Now, you might be asking at this point, why are you using the law of cosines and not the law of sines? Well, I generally tend to favor the law of cosines unless I know two angles in the triangle, and as of this moment here, I don't. So, while all 6 options are on the table, 3 versions of the law of sines and 3 versions of the law of cosines, I'll use the law of cosines until I get 2 angles. So what I'm going to do this time, I'm going to look at this formula here, and my thought process goes like this. Notice the capital C at the end of the formula. Capital C can be any angle that I want it to be. So what I'm going to do here with my capital C is I'm going to let capital C be the angle beta. I could just as easily have let it be theta. It wouldn't matter. But my thought process was, let's let it be either beta or theta, because then I can solve for that angle. So notice, because I chose my capital C to be beta, I'm starting my equation with a side length of 10. Look at the diagram. Angle beta and side length 10 oppose each other. So that's the format needed for the law of sines and cosines. So now I'm going to go about the business of solving this equation for beta. So I can square the 10, square the 12, square the 18.7, and do some other multiplication there as well. Now, before we go on, I want to share a very common mistake among students. I've seen this so much in my career. I've seen people simplify this red expression here, everything on the right side except for the cosine. Students will reach for a calculator and do 144 plus 350.8 minus 449.5, and they'll get an answer. And they'll put that in front of the cosine of beta. But there's a problem with that. The problem is it doesn't follow PEMDAS. Notice there's a multiplication sign here. Therefore, I can't do all that addition and subtraction before multiplication. But what I can do, at least, is combine the 144 and the 350.8, because those terms are like terms in this expression. So those two are combinable, and that gives me the 494-ish that you see there. But I cannot do 494 minus 449 because of the cosine beta and its presence in that last term. Okay, so now how am I going to go about solving for beta? Well, what I'm going to do is I'm going to subtract 494.88670. I'm going to subtract that 494 term from both sides. And after having subtracted that from both sides, I still want to solve for beta. It seems logical to isolate cosine of beta, so I'm now going to divide both sides by negative 449 point, etc. And after dividing both sides by the negative 449-ish number, I ultimately get this, and I've isolated the cosine of beta now. At this point, I can solve for beta itself by simply applying the inverse cosine to both sides. But this raises an interesting question. Is this a valid move? Well, in general, no. It is not generally allowed in trigonometry in general, and I'm not talking about triangle solving here, but in general, it is not necessarily valid to say that if the cosine of beta is something, that beta is necessarily the inverse cosine of that thing. That's not a valid move in general. However, you'll recall that the inverse cosine is defined to be that angle between 0 and 180, or 0 and pi if you're in radians, that has a specific cosine value. So while this is not generally a valid move in equation solving, it is a valid move if we happen to know that beta is an angle between 0 and 180. But in a triangle, every angle has to be between 0 and 180. There's no such thing as a triangle with an angle lower than 0 or higher than 180. So the process of applying the inverse cosine is a valid one in all triangle solving situations. Now, earlier in this problem, you saw me express a hesitance to use the inverse sine function. And I avoided using the law of sines because of that. And that's because this same process you see here with the inverse cosine applied to the other side, that's only a valid process for inverse sine if we happen to know that the angle is acute, or between 0 and 90. So inverse sine and inverse cosine operate very differently. And because inverse cosine is a valid thing to apply when you know the angle is between 0 and 180, that's a valid thing to do here. So this process that you're seeing me do with moving a cosine from one side to an inverse cosine on the other is valid, but that same process is not valid for sine and inverse sine, unless you happen to know the angle is acute, but we often don't know that, which is why I shy away from the law of sines. Moving on, typing that into your calculator will give you an angle for beta, which I will round to the nearest degree. So now we have the answer for beta, and all I have to do now to find theta is use the 180 rule. And using the 180 rule for this triangle and solving for theta, I now know what theta is. And I'll round that to 116 degrees. And I now have theta. So what I've done here, well, let me make one comment first. Notice the x value as being very precise, 18 point something followed by 5 decimals. I'm now going to just round that to about 18.7. By the way, the tradition in these problems is to round angles to the nearest degree and side lengths to the nearest tenth of a unit. Every problem is different, but that's the generally accepted thing to do. And you might ask, well, why did I carry that ugly decimal for x around all that time? Do you remember me using x as a means of solving for beta? You don't want to round things prematurely. If I had rounded x to 18.7 earlier in the problem, that could have affected the outcome of beta, and hence theta, and the whole solving process. So a general good rule about decimals is keep several decimal places, 3, 4, 5 decimal places throughout the whole problem, and do all your rounding at the very end. One more comment before we go on to our next problem here. You may be left with a feeling of confusion here, as though you haven't been told an exact process on how to solve a triangle. Well, the problem is every triangle is different in terms of which information is given and where that given information is. And so there's no one general technique to solve a triangle. But the basic idea is this. For any triangle, there are 3 laws of sines and 3 laws of cosine equations you can make. Write out all 6 of them, determine which one may suit your particular situation the best, and then use that one. So let's take a look at another problem in which one angle is known. Again, diagrams are not typically drawn to scale in these types of problems. Okay, so I'm trying to solve this triangle, Solve means to find all missing angles and side lengths, so I'll label them with any letters I choose. And I'm going to start with the law of cosines here. Now, in general, if there's ever any doubt or you're unsure, write out all three laws of sines and all three laws of cosines, and you'll have a full view of what all of your options are, and you'll be able to proceed. Now, again, with experience, you'll stop writing all six of them as you get better and better at these problems. So that should happen naturally over time for some people, and it should happen never for other people. Whether it happens or not, I'm not going to write out all six formulas here. I'm going to start with the law of cosines, and I'm going to start out with the way of choosing my angles and sides that's the most helpful. But remember, you're seeing someone who's been doing these problems for decades here, and you may need to write out much more than you're about to see here. I've decided on this problem that I have to choose what angle C is first, because capital C, the angle choice, influences lowercase c and lets me know what I should start with. Now, capital C here could be theta or beta or 48. If you were to write this out using capital C as either theta or beta, you'd find the equations are undesirable. Correct, but undesirable, because they have two unknowns in them. However, if you choose capital C to be 48 degrees, and notice, by the way, that if capital C is 48 degrees, then this equation starts with x, because x is the side length that opposes the 48-degree angle. Anyways, if you start with 48 degrees, you'll get an equation with exactly one unknown quantity in it. And that's why I chose this one over all the other versions of the law of sines and cosines. This particular equation is actually quite easy to solve for, because everything you see on the right side of the equation in green, that's all simplifiable. And so what I'm going to do is use PEMDAS to simplify that. So I've got a calculator in my hand. I'm finding out that the cosine of 48 degrees is 0.66913. I'm going to multiply that by 17, 12, and 2. Then I'm going to square the 12 squared and the 17 squared, and I'm going to combine all my terms and crunch the whole thing down to a single number. I didn't show it here, but that's something that you could easily do on a calculator. And now this is a very easy equation to solve, because to isolate x, I simply apply the radical property. Notice I'm not putting plus or minus as I would in a normal algebra situation, because I'm not interpreting x as a negative number here. It is, after all, a side length. And now I know what x is. So this was a pretty easy way to use the law of cosines. Well, you may remember on the last problem, when we used the law of cosines, we ended up using the quadratic formula. And you might wonder, well, what's the difference in the situations? Why did that happen? Well, it has to do with the relative position of the known sides and known angles. In this particular problem, the 48-degree or known angle is adjacent to both of the known sides. When that happens, we typically don't need the quadratic formula. Nonetheless, I've used the law of cosines to solve for x. And now that we know x, we can use the same techniques from the previous problem to find theta and beta. And if you're thinking right now, I don't even know what that means, then please rewind this video and watch how on the last video, once we knew what x was, we were able to use the law of cosines again to find beta. And once we knew beta, we were able to use the 180-degree rule to find theta. So without showing any of that here, because there's no sense watching it again, you can always rewind and see that, I'll just give you the end result of that very lengthy process. I skipped a million steps here to not make you have to watch the entire process unfold again. But after having done all of that, not shown here, I now have my values for x, theta, and beta. And I've now solved this problem. Now let's take a look at a problem where we don't have a known angle at all. Here's an example. Again, diagram not to scale clearly. So to solve this triangle means to solve for all the unknown angles and sides. In this case, just all the unknown angles. So I've given them labels. I like Greek letters. You don't have to do that. I'm going to use the law of cosines again. Now, if you're starting to feel in this video like I prefer the law of cosines every single time, that's not the case. And we're going to see a problem soon where I would actually prefer the law of sines to the law of cosines. But in general, I guess I do quite often prefer the law of cosines because the inverse cosine function is usable in all situations, whereas the inverse sine function is not always usable unless we know that we're dealing with an acute angle. And so there's that complication that I'm trying to avoid by slightly leaning in a preference way to the law of cosines. Now, as far as this goes, I have to choose my side lengths A, B, and C, and my angle, capital C. So what should I choose for capital C here? Well, capital C can be alpha, beta, or theta. And it doesn't seem to really matter much in this problem. There's no one way being easier than the other. So I chose capital C to be theta first. But it also would have been a good choice if I chose capital C to be alpha or beta, because any one of those three options would have given me an equation with only one unknown. So no particular reason I'm starting to find theta first here. But let's do the algebra here. So I did my 12 squared, 16 squared, and 5.2 squared. Then I multiplied 2 times 16 times 5.2, and that led me to this equation. Now again, it would be a mistake to do 283.04 minus 16.4 right now, because the 16.4 is being multiplied by something. And so there's no algebraic validity to combining those terms at this point. But what I can do is subtract 283 from both sides, which I've done here. And now I can divide both sides by negative 166.4, which gives me this result. Now, is it valid to take a cosine equation and to convert it to an inverse cosine equation by just moving the cosine away from one side and converting it to an inverse cosine on the other? That is not generally valid unless we know that theta is an angle between 0 and 180. But it's an angle in a triangle, so of course it's an angle between 0 and 180, and therefore that is a valid move in this case. Okay, the calculator will tell me that theta is approximately 33 degrees. So now I know the value of theta. And I'm going to go on to find alpha next. I could have just as easily gone on to find beta. Now the exact same process you just saw me use to find theta, I could do that very same thing to find alpha. I don't think it's necessary in this video for you to see the exact same process unfold again, but what is important here is noting that because alpha is my angle of choice in the last term of this problem, that 5.2, notice what you see in red here, 5.2 is the beginning of the problem. And if you look at the diagram, just to remind you, the alpha and the 5.2 oppose each other. And so that's how one always has to set up the law of cosines. Whatever side length you start with on the left side, you have to end with the angle that opposes that side on the far right side of your equation. Anyways, doing the exact same kind of algebra that you just witnessed, you would eventually discover that alpha is approximately 14 degrees. So now that we know alpha and theta, we could use the exact same process a third time to find beta. But I don't see the point when I could simply use the 180 rule to find beta. So I did that instead. I didn't show my work here, but beta turns out to be 133 degrees. And now we have the answer to this problem. Now we're going to change our focus, and we're going to look at an example where two of the angles are known. We haven't seen one of these yet in this video. We've seen a problem where one angle was known, and we've seen a problem where no angles were known. Here's an example where two angles are known. And again, this is not to scale. So, in order to solve this triangle, I will label all of the sides and angles that I don't know. And let's go about solving for this. The first thing that seems obvious to me, out of all my options as far as triangle equations goes, I'm going to just start by using the 180 rule to find theta. I won't write out the algebra here, but if all the angles have to add up to 180, it turns out that theta is 63 degrees. You'll notice if you were to take a calculator and add up all those angles, they are in fact 180 degrees. And before we go any further in this problem, notice the subtitle here, two angles known. It's worth mentioning that when you know two angles of a triangle, you effectively know all three of them. And so we could call this a two-angle known problem or a three-angle known problem. Those are really the same thing. Now, my preference for whether to use the law of sines or cosines in any given situation. So far in this video, you've seen me leaning heavily on the law of cosines. My general preference is this. I'm going to use the law of sines whenever I know two, in other words, whenever I know all three angles of the triangle. Because the law of sines is something I will really only use to solve for side lengths, side A or side B. Whatever those end up being called. I don't like using the law of sines to find angles, because when you're finding an angle, you don't know whether it's acute, in other words, less than 90, or not. And if you don't know whether an angle is less than 90 or not, this is not a great formula to be using to solve for that angle, because the use of inverse sine is limited in a certain capacity. And so my general rule is, unless I know all three angles, I'm not going to use the law of sines. Or knowing two angles, meaning the same thing as knowing all three. Okay, so now the question becomes, what am I going to choose for capital A, capital B, lowercase a, and lowercase b? Well, you can choose anything you want as long as the capital and lowercase a oppose each other and the capital and lowercase b oppose each other in the diagram. If that's true, then it's completely your choice what to use here. So I've chosen, on the left side of my equation, a 63-degree angle and 10. Notice in the diagram, the 63-degree angle opposes the 10. And on the right side of my equation, I've chosen 21 degrees and x. Notice in the diagram, the 21 degrees is opposite side length x. I'm not meaning to suggest that this is the only way you could go about the problem. I could have chosen the I could have chosen the 96-degree angle here and it would have worked out just fine. If you're ever in doubt, what should I use? I don't know how to start a problem. Write out all 6 equations, 3 laws of sines and 3 laws of cosines. Because some students, and you may be one of them, need to see all 6 equations to see which ones are the most viable. Other students, or me with decades of experience, I don't need to write them all out. But keep in mind that that's always an option for you if you're ever staring at a problem totally stuck on how to begin, and that can happen. Okay, now that I've set this up, Notice it's a viable equation because it has only one unknown in it. Let's go about the business of solving. What I like to do on these problems is use the cross multiplication trick, because that eliminates any fractions, and now I don't have to deal with fractions anymore. Okay, since I'm solving for x, it seems logical to divide both sides by the sine of 63, which I've done here. And now I have a calculator in my hand. According to my calculator, the sine of 21 degrees is 0.358. The sine of 63 degrees is 0.891. Plugging those two decimals into this expression and calculating all of it as one single answer gives me a value of x. And now that we know x, the only remaining thing in this diagram, notice in the upper right corner, the only thing we don't know at this point is y. So how are we going to go about solving for y? Well, at this point, there's a lot of ways, and I'm not going to show you any of them. But the stuff that you've seen in this video will certainly suffice, and there's many options that you have to solve for y here. One would be to use the exact same law of sines procedure you just saw, but incorporating the 96-degree angle this time. Because if I incorporate the 96-degree angle in one way or another, that's going to get a y into my equation. Anyways, I leave it completely up to you to figure this out on your own. If you feel like you need to pause the video now and find y yourself, now wouldn't be a bad time to do that. And if you did pause your video, what you should have found is that y is about 11.2-ish. And now that I've got my answers, I've completely solved this problem. Now, again, these aren't wrong answers, but it's not typical to have so much specificity in decimals out to the nearest 100,000th or whatever we've got here. And so typically the tradition, and it depends on your professor and the situation, but the tradition here is to approximate to the nearest 10th. At least if you're in my class, that's what I'll be asking you to do. So now what we've covered in this video so far is we've covered how to handle situations in triangles where there's one angle known. Then we covered the no angles known. And we ended by covering a situation where two, in other words, all three angles were known. Now this seems to cover all the scenarios that you may encounter. But I want to take a look at another problem where one angle is known. Why are we going back to this? Well, this problem is different in that, yes, one angle is known, but it's going to turn out that there are two triangles that match this description. I don't expect anyone to see why that's the case yet. We will as this problem unfolds. Let me say that another way. If I told you that you were to go build a triangle with a 52-degree angle in it, and side lengths of 18 and 16 where shown, it turns out in the physical world, you could build two completely different triangles that meet these specifications. Now, as a student in a math class, when you're given this problem and told to solve it, you don't know that there are going to end up being two triangles that match this description. It just looks like any other problem to you. So we're going to start this problem like we started the last problem with one known angle, by labeling everything and using the law of cosines. Again, there are ways to use the law of sines to do this, but I don't particularly like the law of sines when I only know one angle. That's just my preference. Most other professors and other videos on YouTube would have you using the law of sines in this situation, but I think it adds a degree of complication that we don't need, as we've discussed before. So leaning to my go-to formula when one angle is known, law of cosines. Now the question with law of cosines always is, what do you want the capital C at the end to be? The only angle in here. And if you're unsure, you'll have to write out all three options, where C is 52, where C is beta, or where C is theta. But one thing you'll notice, if you were to write out all three of those, only one of them would have a single unknown. The others would have two or more unknowns. And so the one that I ended up keeping, essentially, is the one where capital C is 52. And it makes logical sense. If we know an angle, why not use it in the law of cosines, right? If it's the only angle we know, plug it in. That's what I like to do. Now you'll notice this equation has a single unknown in it, and that's x. So we're going to go about solving this just like you've seen before in this video, using the quadratic formula. First, some simplification. I did 16 squared, 18 squared, and 2 times 18. And then I saw that these were two factors in the same term, so I got a calculator. According to my calculator, the cosine of 52 degrees is 0.6156. Using that decimal times 36 gives me this number. Now, because I have an x squared in my equation, you'll again remember from algebra that setting our equation to 0 is the most efficient strategy in these quadratic situations. So I'm going to subtract 256 from both sides, thereby setting my equation to 0. And rearranging the terms just because it helps me visually to use the quadratic formula when I put my polynomials in standard form. I'm ready to now use the quadratic formula. And so, plugging in A, B, and C into the quadratic formula ultimately leads me to two answers. Now you'll recall that the quadratic formula has a plus or minus symbol in it. And because of that plus or minus symbol operating as two separate symbols, we always get two answers for the quadratic formula. Okay, well this looks very much like what we saw earlier in the video, but something is different here. You may recall the last time we used the quadratic formula, we got a positive answer and a negative answer, and we discarded that negative answer earlier because we were looking for a positive side length x. But in this case, we got two positive answers. So whereas we may have not known at the beginning of this problem that it was going to turn out to be a two-solution problem or a two-such triangle problem, we now have evidence that there are two triangles that match the description in the upper right corner. What does that mean exactly? Well, let me juxtapose the original problem next to our two values for x. How can it be that x is two different values? Well, because this diagram is not to scale, it's kind of hard to see it. So what I've done is I've actually taken computer software and I have physically made actual to scale drawings of what these two situations will look like. This is not something that I expect you to do, nor would any professor, I'm assuming. But what we've discovered here, because we got two positive answers to the quadratic formula, we've discovered that there are these two situations. And again, I've drawn them to scale here just so you could see. Now, unlike in the top diagram, notice the upper right corner with the 52-degree angle. That angle, that physical size of that angle is actually 60, because that's just the way I draw everything, 360-degree angles, just for simplicity. However, in the bottom two diagrams, those two angles in the left corner, they both are physically, actually 52-degree angles. And the 18s and 16s in each diagram, those are, on my screen anyways, and maybe not yours, those are physically 18 millimeters and 16 millimeters respectively. So these are actual two-scale drawings of these two completely different looking triangles.
that both match the description of the diagram in the upper right-hand corner. They both have a 52-degree angle in the bottom left. They both have an 18 millimeter side on the left side, and they both have a 16 millimeter side on the right. And so whenever you get two possible answers for x, in other words, whenever the quadratic formula gives you two positive answers and hence two viable answers, you don't have to draw out the pictures, but you have to understand that there are two physically different triangles that match the description. That is the meaning of getting two answers for x. Okay, now that we have a sense for what that means, let's continue to solve for theta and beta. So what do you do next? Well, at this point, you have to treat the problems as two completely separate problems, because theta is going to turn out to be very different in each case. Notice in the right side of the screen, theta appears to be a very small angle. And likewise, beta appears to be an obtuse angle on the right side and an acute angle on the left. Now, you wouldn't necessarily know that unless you'd drawn them to scale, but the math will let you know what theta and beta is. The point is you have to solve these problems completely separately and unrelated at this point, now that we know there's two values for x. So how do we go about that? Well, I won't show you in this video, but in all the techniques that we've seen up to this point, you have the skills at this point to solve for theta or beta, or both. I would recommend still using the law of cosines at this point, because in each case, I still only know the 52-degree angle. I don't know theta or beta. So my strategy in each of these would probably be use the law of cosines to find theta in each case separately. And once you know theta in each case, you can use the 180-degree rule to find beta. Or find beta first and then use the 180 rule to find theta. I won't show it here, but it's something you could pause the video and do if you'd like, because the answers are about to appear. Pause the video and try it yourself if you're up for a challenge. And whether you took that challenge or not, here are the end results. And if you're still thinking, how on earth did he get those? Rewind the video and see how I was able to use the law of cosines to find a missing angle. Either which way, we now have our results, and you'll notice that because of the particular situation that we're in, we have two completely sets of different answers for x, beta, and theta. And that completes this lesson. Thank you so much for watching.